In this video, I'm going to examine the concept of invariance, proper time, proper velocity, and proper momentum in space-time algebra. Space-time algebra is the geometric algebra that is formed over the Dirac basis, the gamma matrices, or gamma, not gamma 1, gamma 2, gamma 3, that are defined to have the dot product, gamma mu dotted with gamma nu, is g mu nu. And in this case, g mu nu is 0 when mu is not equal to nu, all the off-diagonal terms, and is 1 for g0, 0, and is minus 1 for any of the remaining diagonal terms. This would sometimes be written as, we would write that g mu nu has a matrix representation of 1, minus 1, minus 1, minus 1, zeros everywhere, off diagonal. So that is the defining relationship for our basis for the space-time algebra basis. Given this, in geometric algebra, that dot product, g mu dot g nu, is just the symmetrized product of the two. So that is gamma nu plus gamma nu gamma mu. This is also, in quantum field theory, Q of t, you would use this here equals g mu nu as the defining relationship for the Dirac matrices. Whereas in space-time algebra, we have the same relationship, but we just call it the dot product. So this is the dot product. This is a standard dot product. So in geometric algebra, we take two vectors and we multiply them together. We get a dot b plus a wedge b, and BA is b dot a plus b wedge a, which is minus a wedge b, and you can merge these together to come up with a dot b is half of ab plus ba, and a wedge b is half of ab minus ba. So this is our not a defining property in geometric algebra, but just a consequence of our definitions. And in space-time algebra, we take g mu dot g nu as g mu nu as our defining the definition of length in this algebra. So with such a definition of length, we are now free to do some computations. So if we are to, we have this kind of the simplest thing we want to compute. Let's take a vector, say a position vector with coordinates x mu. And if we take the length of this, then it is going to be, so x squared, x dot x is x mu gamma mu dot x nu gamma nu x mu x nu gamma mu gamma nu, so x mu x nu g mu nu. So this is what we would, in a tensor representation of relativity, is our familiar expression for the length of a vector. And there you would write it as x mu x nu, as x mu x mu, where x lower mu is x nu g mu nu. So this is our lowering operation in tensor algebra, and in this case, in geometric algebra, it just gives us a way of defining a lower index quantity relative to an upper index quantity. And we always find that we should have, well, we we should end up with matched indexes if we revert to coordinates. And so actually, we're actually free to write our vector. If we wrote our vector as x mu, we could say that is x mu g mu mu times gamma nu. So that is x nu t mu nu gamma nu. So we would define this quantity as our reciprocal frame vector. So that is x mu gamma upper index mu. So upper index mu is g mu nu gamma nu. So in this case, we have gamma 0, it's gamma 0, gamma 1, it's minus gamma 1, gamma 2, it's minus gamma 2, and gamma 3, it's minus gamma 3. So we can summarize these kind of relationships as g mu dot g nu is delta mu nu. So here's the kind of an ad hoc way of going between the geometric algebra and tensor forms of a position in upper or lower indices, and the distinction of sometimes in tensor algebra you would call this I think the covariant index when it's upper and the contravariant index when it's lower. But in geometric algebra, we always have the upper and lower index quantities paired. Either way, it represents the same vector x. So whether we use upper indices or lower indices, it's kind of irrelevant. And it represents a single vector x regardless. It's just a choice of basis as opposed to anything with specific meaning. So if my point here, okay, so I was looking at the dot product of x with itself. So we found that x dot x was x mu g mu nu. So that is just going to be x0 squared minus x1 squared minus x2 squared minus x3 squared. And having our both indices and power together in a square is kind of awkward, but so be it. So here's our dot product expanded out in coordinates. And one of the things that we have to care about here is that if we are to make a change of basis, it should not affect this end result. So this end result was that if x was, let's call it x naught as ct, so this was ct squared, our time-like component, minus our spatial component squared. This quantity should be invariant to change of basis. Now, in particular, let's suppose that we had x was c tau gamma naught prime. So in some frame, gamma naught prime, gamma 1 prime, gamma 2 prime, gamma 3 prime, we can make a transformation from our original basis to this new basis. And if we do that, that transformation could eliminate all of the spatial components of the vector. And so now, if we take x dot x, it is just going to be c tau squared. So there's some frame where our vector length, we have time in that frame, c tau squared is ct squared minus x squared in our opposite frame. So we have a relationship between the time, the proper time, the rest frame time, and time in an alternate frame where there is a component to the, so if we're looking at this time and say space, then the motion is strictly up the time axis. And so that's what we call this the rest frame. It's moving only in time, it is resting in space. Let's look at how this translates to velocities. So if we were to take a 4-vector x, x mu gamma mu, and take its derivative with respect to time, then we have a weird, this is not going to be an invariant quantity because time is not an invariant quantity. So our change with respect to a non-invariant quantity is not invariant. So we want an invariant time. So this is kind of an undesirable non-invariant. So what we do instead is we take our derivative with respect to proper time, assuming that we can compute that. So now we have dx mu d tau x mu, which is dx mu dt d tau. And we should expect that this quantity will be invariant. And we can actually compute that in the rest frame. So in the rest frame, dx d tau is c d tau gamma naught, which is just c gamma naught. So dx d tau squared is just going to be c squared. So our velocity, our proper velocity squared, is just c squared. It is an invariant quantity regardless of the frame. So we know that this is the in the rest frame. So if we presume that that's true in any other frame, and I guess we should look at how we presume that's the case. So let's suppose that, imagine we rotate in, we can rotate in space, let's say by an angle theta. So that is going to be e to the I theta by 2, x e to the minus I theta by 2. And here I is something like gamma 1, gamma 2. So if we're rotating in the xy plane, so this is for xy rotation. Or we can rotate in space-time. Let's say our alpha for rapidity is e to the minus, or the sign varies according to whether you want to do a active rotation or passive. We'll say that is j alpha by 2. And now suppose if we're rotating in the CTX plane, so j is going to be gamma 1, gamma naught. So gamma 1, gamma 2, if we compute its square, we find that is minus 1, whereas gamma 1, gamma naught squared is going to be plus 1. So it means that rotations that are in space-time are hyperbolic, whereas rotations that are in space only are trigonometric. And so if we were to write out this in its matrix representation, we'd find sines and cosines. And if we were to write out this in its matrix representation, we would find that we have coches and sinh. But regardless of the form of this operation, we can say that some rotation x equals e to the b by 2 x e to the minus b by 2, where b is a bivector. So b is a bivector. So this is a general rotation in space and time. And let's see how that changes or leaves the same a dot product. So if we have a dot product and we rotate, so we're transforming to the rotation in space or time, or in space or in space-time, that is just going to be the scalar part of the square, the rotated or Lorentz transformed quantity, which is e to the b by 2, x e to the minus b by 2, e to the b by 2, x e to the minus b by 2. Take the scalar part, and here we have a 1, so we're left with e to the b by 2 x squared, e to the minus b by 2. X squared is a scalar, so we can pull it out. We're left with x squared, e to the b by 2, e to the minus b by 2. And what do you know? We're just left with x squared. That's x dot x. So rotating in space or rotating in a space-time plane, in both cases we have the same quantity where they are space-time distance preserving, and that is the justification for saying that our proper velocity is an invariant quantity. So there's some rotation that we can make that will eliminate the spatial components of the vector, and if we do that, then we just get c squared as our proper velocity squared. And let's see how dx d tau in a different frame is then translated. So if we return to dx d tau, we found that that was dt d tau dx mu dt gamma mu. So if we square, square this, we have dx d tau, we'll call this v, so v squared, and this frame is going to be dt d tau squared times dx naught dt squared minus the sum of dxk dt squared, which is dt tau squared times ct dt, which is c squared, minus our velocity squared. This is velocity in just taking all of our, we have dx1 dt squared plus dx2 dt squared plus dx 3 dt all squared, which is just our velocity squared. So we see that we have c squared and v squared, and on the other side, v squared equals c squared. We're left with dt d tau all squared is c squared divided by c squared minus v squared, or dt tau is 1 over the square root of 1 minus v over c squared. We have the Lorentz factor, what we would call gamma, in any book on special relativity, 1 over the square root of 1 minus v squared over c squared. This quantity just naturally pops up, just based off of the properties of our basis. So our basis implies this an implication of our choice of basis is that quantities like that just fall out. And so we can now go and write our proper velocity is 1 over square root of 1 minus v over c all squared times was c gamma naught plus the kth component of our velocity, so that ek was dx k dt, the spatial velocity. So we would write our velocity as dxk dt ek. But now we have a split in terms of we don't have our ek basis here. We have our gamma basis, which squares to minus 1, unlike these, which square to. So we had ek squared is 1, but we have gamma k squared is minus 1. Let's look to see if we can establish a correspondence between our gamma basis and our spatial basis. And to do that, let's take dot and wedge products of our proper velocity with gamma 0. So if we dot with gamma 0, these components will be killed. If we wedge with gamma 0, these components will be killed. So we're left with v dot gamma 0 is c over 1 minus v over c squared, and v wedged with gamma 0 is vk gamma k gamma naught divided by 1 minus v over c squared. Now this is almost a familiar looking quantity. We just have to look at this bivector. So that bivector, gamma k gamma 0, if we square that, we have gamma k gamma 0 gamma k gamma 0, and let's say flip the order of one of these terms. So that is minus gamma 0 gamma k times gamma k gamma 0, which is minus gamma 0 gamma k squared gamma 0 is minus gamma 0 squared times gamma k squared, which is minus 1, which is just 1. So what do you know? Our bivectors in the Dirac space-time algebra basis, if we take a space-time plane, unit space-time plane, and square that, we end up with 1. So these, we can say that this is isomorphic to EK, or identical. We can define our EK as this particular pair, and in particular, so if we looked at v dot gamma naught, that was our gamma factor time. I'll break it out since it's confusing to have. So that was c over square root of 1 minus v over c squared, and v wedged with gamma naught is v wedged with gamma naught is vk ek to the square root of 1 minus v over c all squared, which is velocity over 1 minus v over c squared. In particular, we can go and look at what our proper momentum is going to be. And we just make some more space here. So if we take our proper momentum, mv, which is m dx d tau, well, now we have so let's say that P equals mv. So P dot gamma naught, the time-like component of momentum, is mc over the square root of 1 minus v over c squared, and P wedged with gamma naught is mv over 1 square root of 1 minus v over c all squared. So what do you know? This is our relativistic momentum. So that is our m d e d tau. What I was hoping to get to was a justification for the identification of our Euclidean basis as its bivector representation. So if we now see that in space-time algebra, if we want to represent the spatial component of something, we wedge with gamma naught to get the spatial component with respect to the rest frame of a stationary observer in that frame. And if we do that, it's going to be observer dependent. So if we were to make the same wedge product with respect to a different gamma naught prime, we'd get a different value. So that's a fundamental tenet of relativity, is you get different values depending on whether or not the frame that you're operating with is moving or not. And so we see that a consequence of trying to pick out that component, that we find that we get the correct relativistic momentum just by virtue of having used the Dirac basis, but then wedging with the gamma naught of the frame of that we're interested in. So this was a long-winded justification for picking gamma k gamma naught as our bivector basis for the spatial component of a four-vector in space-time algebra. And having attempted to justify that, we're now going to be able to use that in some subsequent videos. In particular, one for Maxwell's equation, where we will see that these bivector basis elements will be of use. And that is it for this video.